So now, just like we did with capacitors, where we looked at capacitors in series and capacitors in parallel, we're going to look at resistors in series and resistors in parallel. And we'll have some similar rules like we did for capacitors regarding the equivalent resistance and regarding the potential and the current in those capacitors. So let's first just start off with this. I can show you, it's fairly simple to derive what is the equivalent resistance of two resistors in series. So I'm just going to show it to you here. I've already shown that delta V is equal to IR1 plus IR2. That's just because of this idea that if I return back to the same point, then my change in potential is going to be 0. My electrons will have the same amount of energy when they return back to the same point. And that's where this expression comes from. And so I can factor out that current because all the resistors in series have the same current. That's going to be one of our rules. I'll write it down soon. R1 plus R2, just factoring out that current because it's identical for both. And so, delta V is equal to I times the equivalent resistance. So this gets us our first rule for resistors in series, and that is that the equivalent resistance equals R1 plus R2 plus, however many resistors you have. Now be careful, because if you recall, for capacitors in series, it wasn't so. It was, you had this inverse of the sum of the inverses, that 1 over C1 plus 1 over C2. That was for capacitors in series. So for resistors in series, it's like capacitors in parallel. The equations are on your equation sheet, so if you just forget, just look. But this should be something that you internalize and store away in your long-term memory so that you can just have it at will. Now, the equivalent resistance, which should be obvious to you, is always bigger than any individual resistor. It's always bigger. So that's like a little sub-rule. So we'll call this rule number 1. And this is just, it's not inconsequential, but we'll call it 1A. And it should be fairly obvious to you that the equivalent resistance is always bigger than an individual resistor. Some other rules about resistors. Resistors in series have the same current. If we're imagining, our circuit like a water pipe, I have a certain amount of current flowing through this wire. That amount of current goes through that resistor, and that amount of current also goes through that resistor. All right? Also, something that we're going to call the loop rule, which we'll use soon, is that the change in potential across resistors in series adds to equal the change in potential across the battery. Adds to equal the voltage or the change in potential across the battery. Now, this is just like we had with capacitors. When we had two capacitors in series, we said that the sums of the potentials across those capacitors had to equal the potential across the battery when the capacitors were in series. So this is same as it was for capacitors. Okay, so let's consider these two light bulbs. They're hooked up in series. Now, first of all, what happens if I take out this light bulb? If I remove R2, what happens to the circuit? Well, if that happens, if this is a true series circuit. Now, most of your Christmas lights, by the way, which might look like this, they're not really series circuits, or they might be a series circuit, but they're slightly different. They have some modifications. But if it's a true series circuit, if R2 is removed, that light bulb is removed, then R1 will go out. It will no longer have electricity flowing through it. Now, what happens if R2 is replaced with a wire? What's going to happen to R2? Well, a couple of things are going to happen. All right, first of all, what's going to happen to the equivalent resistance? Is it going to go up or down? Right. The equivalent resistance is going to go down. All right, and if I think about this, V is equal to IR. Or, first, before we think about it mathematically, let's just think about it intuitively. If I now have less resistance to the flow of electricity, how is that going to affect the flow of electricity? Well, if I have less resistance, then I'm going to have a greater flow of electricity. So I can see that mathematically as well. If R goes down, I goes up. So if my equivalent resistance goes down, the current increases. And since I know that power equals V times I, if the current increases, or actually, the better way to think about it, the power is equal to I squared times R. The resistance is staying the same. Current is increasing through that light bulb, so the light becomes brighter. We'll see some similar questions to that in the quiz, the online participation quiz. We'll stop here and come back to this circuit in just a moment.